Morning to everyone. Today we will take a look on how the speed of asynchronous or induction motor can be controlled by means of AC drive. So what we have on this test bench? First of all, we have this induction motor, quite small. It is only 300 watts, but it's full enough for our needs. Further, here we have a AC drive. The AC drive will help us to control speed of this induction motor. And also we have this load, in this case this is the alternator, so typical alternator, DC alternator, but it's not connected, here's the wires, and it's not connected, so this is just some load which is not connected, and we are not interested in it, So on this induction motor, this is the squirrel-cage motor, and on this induction motor we have contacts, terminals. So these are already unscrewed, so I can remove this cover, and here we can see its terminals, U, V, W, and so on, as well as 3 wires. These 3 wires goes from here, and these 3 wires get power from the AC drive. So if I will remove this cover, here is the nodes A, B, and C faces, A, B, and C, U, V, and W, A, B, and C faces. So we can remove this cover, and you will see A, B, and C phase. Of course, this color is not correct. This is not a grounding, this is the C phase, The AC drive by itself get power from these 2 wires, L1 and L2, So these 2 wires are connected here, and further through this brown color wire we can get power from the wall socket. Okay, so I will put this cover back because for the safety reasons, Okay, here's the cooling, These additional contacts are used to remotely control this AC drive, but in our case we will not use it. Also, it can be remotely controlled by means of network module, which can be installed here, but it's not installed and we will not touch it. Okay. So this motor is connected as a delta because this AC drive supplies 230 volts, No, this is the input as well as this is the output, 230 volts. And if we will take a look onto this motor, we will see that in order to operate at 220 volts, we have to be delta connected, delta connected, serial. If you don't remember how to make delta connection, then you can look from the back of the cover, and most probably you will find this hint. From the left we have delta connection, and from the right we have star connection. And here is the how do we have to connect these pieces of metals. In this case, 3 pieces of metals are connected like this. Okay. Also from the back we have a cooling fan. It sucks air from the back, then it goes into the centrifugal fan. It's already unscrewed. I removed these screws. These are here. So air goes inside, then it's rotated by means of this blade, and it goes outside. But it's not able to go outside from here because here is the wall. And therefore it is folded and further goes through these heat sinks, yeah? So it becomes cold. In my case, I have to remove it because I have to access some rotating part in order to measure the speed. Here is the reflector, so I will use this reflector in order to measure the speed by means of this light, yeah? Okay. So now let's take a look how do AC drive control speed of the motor. In order to better understand what is going there, I had connected a voltmeter. So the voltmeter is connected between two phases, so we will get line-to-line voltage, which in our case is 220 volts, yeah? 220 because I have set this value inside because this is the rated voltage of this motor, 220 volts, not 200, sorry. And also we will be able to see current which flows through the A phase. So wire from the AC drive, yeah, and two wires goes into the terminal block, and the third wire is folded back, then through this blue wire into the ampermeter, and from the ampermeter back into the terminal block, and then to the A phase, yeah. So that's how it is connected. Ampermeter is set to 2 amperes, so the full scale range is 2 amperes. And the voltmeter is set to 300 volts, so the full scale is 300 volts. So here we have to multiply it by 2, and here we have to divide by 5. So okay, now let's see how does it operate and what will happen if I will enable it. First of all, I have to supply power, and then it will start. Okay, so the most efficient way how to control speed of induction motor is to adjust the frequency. The frequency can be adjusted by means of this potentiometer, as well as frequency can be adjusted by means of external contacts, as well as it can be adjusted from the keyboard. In my case, it is set to be adjusted from the keyboard. So I can enter inside and I can adjust the frequency, for example 40 Hz or 50. Yeah. Remember that this motor is 50 Hz rated. So now I can press the run and the motor will start. Look onto the voltage and current. As you can hear, it starts very slowly. This is because the AC drive provides function of the soft start, so it adjusts frequency smoothly, and in a similar way it provides braking action. Of course, you can select different time for the acceleration, for the deceleration, as well as different type of braking. For example, just to remove power, and it will brake by itself without this assistance. So once again, okay, at the rated frequency of 50 Hz, so I can put it into my table, yeah. At the rated frequency of 50 Hz, this is the number of measurements. So 50 Hz, we consume 2 amperes. Yeah, exactly 2 amperes. So we consume 2 amperes. And the supply voltage is 110 times 2, then 220 volts. So this is the rated frequency. Therefore, voltage also is rated. This motor is 220 volts rated. And the motor consumes 2 amperes. What about the speed? Since this motor has 2 pairs of poles or 4 poles, it should rotate approximately 1500 RPMs. (1491) because of sleep it's slightly less, yeah, because the 1500, this is the synchronous speed of the field, and the speed of the rotor is slightly less, yeah, due to the sleep. So what will happen if I will reduce the frequency? The problem is that in this case current must increase. Look, here is the representation of the equivalent circuit of the armature winding. So the armature winding, of course, has its own real active resistance. It's very small, but it exists. The problem is that this is the winding, and the winding is wounded, and since it is wounded, it has some induction. Since it has induction, then it has also reactive or imaginary resistance, XL. This imaginary resistance depends on the frequency. Lower frequency will cause lower resistance. That means that if I will reduce frequency, then this will reduce, and therefore current will increase. And this is the problem, because this motor is rated to 2 amperes. So if I will reduce the frequency, say, twice, then current will increase, taking into account this, maybe in 1.5 times. But in this case it will be greater than rated current. In order to overcome this problem, AC drive will reduce voltage in order to keep our current within allowable limits. So look, I will enter 25 Hertz, so it should to slow down approximately twice. Now I will confirm and look onto the indication. So current is still approximately slightly more than 2 amperes, yeah. But the voltage has been reduced approximately twice. So current is still 2 amperes, but the voltage now is 60 by 2, slightly less, yeah, 59 by 2. This is the 108. Okay, what about the speed? It should to drop twice. Let's check. No, yeah, 745, so approximately twice. If I will reduce the frequency even more, down to 5, then our motor will rotate very slowly. And the voltage which is applied is quite small, yeah. So 5 Hertz, and the supply voltage is very small, approximately 15 by 2, 30 volts only. And the current, slightly less than 2 amperes. This is due to the fact that AC drive starts to generate current, because now cooling fan is moving very slowly, yeah, and therefore cooling of the motor is very inefficient, and therefore we have to reduce current even more than the rated current in order to prevent its thermal damage. What about the speed? I'm not sure that it will be able to measure it. No, 146 revolution per minute. So now what will happen if I will increase? Now first of all, let's go back to the rated frequency. Okay. So now what will happen if I will increase frequency for more than rated frequency? In this case, fully theoretically, it has to apply higher voltage than 220 volts in order to save current. The problem is that motor is rated to 220 volts. If the AC drive will apply higher voltage, it means that it will cause overvoltage of the motor. That's why in a further RPMs, which are higher than the rated, it will keep 220 volts. Yeah? Otherwise it will cause overvoltage and can damage insulation of the windings. So let's see what will happen if I will enter, let's say, 75. So voltage remains 220 volts because we can't apply more, yeah? Otherwise we will damage the winding. But what about the current? Current now drops by half, yeah? Now it is only 2 ampere full scale, so now it is only 1 ampere. This is due to the fact that we had increased frequency from 50 to 75 Hertz. So the resistance of the induction increases and therefore current reduces. So current reduces. Speed should increase proportionally to the frequency. Let's check. Yeah, 2236. And now let's increase frequency 2 times. 2 times, this is the safe 100 Hertz. So this is the safe limit for the small motors. So you can call 200% overspeed without any warnings. Yeah. So now I will apply. So now it should operate 2 times faster than 1500 RPMs. Yeah, 3000. Of course we have to take into account the sleep. 30 RPM goes into the sleep. So this is the rating, yeah? And the voltage still is 220 volts. And the current reduces even more. So now it is 0 point. I have to, yeah, 0.65. So if you will construct the graph, then you will see that below rated frequency, voltage is much more lower. Yeah, for example, at 25 Hertz frequency, voltage is only 110. Whereas at 50 Hertz frequency, voltage is rated. Above the rated frequency, voltage is kept at the rated value. Yeah? What about the current? Here is that we got inverse situation. Up to the rated frequency, we have rated current of 2 amperes. And above the rated frequency, the current starts to reduce. 75, we got 1 and even less. Yeah. So torque is proportional to the armature current. Therefore, we can say that if we are operating below the rated frequency, then our motor is operating in a constant torque mode. If we are operating above the rated frequency, then mechanical power, this is the torque times speed, yeah, 2pn in revolution per second, yeah. So speed increases, but current drops, so torque drops. So speed increase, torque drops, so the power is not changed. So this is the constant power region. So below the rated frequency we have constant torque, so power drops, and above the rated frequency we have a constant power region. So now I have left 8 minutes, so I would like to show you how do AC drive produce the frequency which is set here. So let's set, for example, 30 Hertz, yeah. So how do it produce it? The problem is that actually it rectifies power supply into the DC, and from the DC it should to create AC. The problem is how to do this. So actually here is a lot of transistors, yeah, no, at least 3 for each phase, at least 1, yeah, but typically much more, at least 6. So this is the voltage and this is the time, yeah. If the transistor is fully open, then we got rectified voltage. In our case this is 310 volts, because we are rectifying 230 volts by means of full wave rectifier. And if the transistor is closed, then we got 0. So look, open, close, next, open for the longer time, close, next, open for the longer time, closed, then open for the shorter time and open for the even less shortened time. So here the period between pulses is constant. So this is the so-called, if we divide this period by 1, if we got inverse from the period, then we got frequency, yeah. So this is the carrier frequency. In our case it is 2 kilohertz, but I can select the even higher. But the duty cycle, which is the pulse divided by the period, yeah, it is variable, whereas this one is constant. So the average voltage, if we will take it, yeah, here it is very low, then it is increases, then it is increases because the pulse becomes wider, then it reduces because pulse reduces time, yeah, then becomes lower, and so on. So we got such virtual half of the sine wave. In a similar way we can construct the negative part. This is so-called PWM modulation, or pulse width modulation. So in order to show it, I will use this old style oscilloscope. This is due to the fact that actually we do not have the ground. So I do not have the place where to connect the ground. So voltage is applied here, but this is the A phase and this is the B, this is the B phase and this is the C phase. So, okay, this is the phase, but where to take the ground? I do not have ground, so I have to connect ground wire to the second phase. If you will do it for the modern, properly grounded oscilloscope, you will just burn it out. Don't do it, yeah? Because this is also the phase, because we have delta connection instead of star. So starting up, and look what we got. Yes, of course it's blinking because it's blinking onto the camera because it is analogous, yeah. But you may see that we got negative half wave, positive half wave, negative, and so on, yeah. I can move them. So if you will take closer, then you will see that here is the 0 level, and here is the 1, 2, 3 with half centimeters. My voltage is set to 10 volts and plus 10 times divider. So 1 centimeter, this is the 100 volts. So 100, 200, 300, 10. So this is the maximum voltage. From 0 to 310. So this is the DCL, DC line voltage. If I will extend it, no, under the camera it's not very good, yeah, but maybe, oh yeah. You can see that here is the pulse width is shorter and here is the pulse width is bigger and the pulse is lower, yeah. If I will extend it more, then you will see that pulses are not rectangular like I showed here. This is because motor has induction, and this induction does not allow us to get sharp pulses. Let's try to extend even more. No, now we can't synchronize, yeah. And of course, if I will increase the frequency or if I will reduce the frequency of this resulting waveform will increase or reduce. So for example, let's put 400 Hz. Shorter period, so higher frequency. Even more shorter period, yeah. It's hard to stabilize. Now I will switch it off and it will gradually reduce frequency, yeah. So you'll see how it looks. And now it's stopped, yeah. So that's how PWM looks like, yeah, theoretically, and that's how it looks like in a real life, yeah. So yeah, here is the results. So thank you.